Hello, my name is Daniel Grimmer, and this is a video abstract for a paper I just put out titled A Discrete Analog of General Covariance. Could the world be fundamentally set on a lattice? What I do in this paper is to consider lattice theories quite generally and come to some understanding of how we ought to interpret the lattice structures that they seem to imply are underlying the world, right? So, to give you an example of the sort of thing I'm thinking of, consider here the continuum heat equation, where the derivative in time of this field phi is proportional to its second derivative in space, right? So this is a very standard equation used in physics. It's just an example here. And consider two discrete versions of this, which are set on a square lattice, as you can see on the left, and a hexagonal lattice on the right. If we have nearest neighbor interactions for these equations, then these are the corresponding theories. So the derivative in time is proportional to something like the derivative in space, or the closest thing you can get to it with nearest neighbor interactions. So, what would it be like if the world was really like this? Right? Suppose the world really was on a lattice like this. Intuitively, it could be. The world might be fundamentally set on a lattice. Indeed, some considerations from quantum gravity seem to point towards this. By investigating the world on the smallest scales, it might be the case that we discover microscopic symmetry restrictions, right? In a continuum, we could rotate continuously, but we might find we can only do quarter turns or sixth turns, which preserve the dynamics, right? And intuitively, if you found something like this, it would be a lattice artifact, right? Which reflects the discrete symmetries of the underlying lattice structure, right? Quarter turns for the square lattice, 1/6 turns for the hexagonal lattice. Right. And so say we then believe the lattice structure theory, right? And we might further investigate and try and discover what kinds of interactions there are on this lattice. They could be nearest neighbor, like I showed before. They could also be longer range. They could be next to nearest neighbor or infinite range. And intuitively, you could go and do microscopic investigations and discover what kind of lattice there is and what kind of couplings there are on the lattice. All of this seems like metaphysically plausible, right? And suppose all that happens. Suppose that after much empirical investigation, we find such lattice artifacts, right? And moreover, suppose that we ultimately have great predictive success when we model the world as being set on, just for instance, a square lattice with next to nearest neighbor interactions. Suppose that theory works. That just theory works and it applies to the world very, very well. Would this prove that the world is fundamentally set on a lattice, right? So would it prove that? Would it even be good evidence for it? No. All that it would prove is that the dynamics of the world can be faithfully represented on such a lattice with such interactions, at least empirically. That doesn't go anywhere towards showing the world actually is like that, right? Anything can be faithfully represented in any number of ways. I might describe the motions of a pendulum with the movements of circuits, of electric currents in a circuit, or vice versa. Circuits can be explained or modeled well, perfectly in fact, with pendulums, right? So we have to do extra empirical work to know which representations we should take seriously, which parts of our theories are substantive, and which parts are representational. We really need to do a lot of interpretive work to come to these things on top of any empirical concerns we may have. So, what reasons do we have then for taking lattice structure seriously, besides the fact that maybe it works very well to describe the world? What reasons do we have for taking it seriously on top of that? Well, the following claims about lattice structure seem to suggest that it plays a substantive role in these theories, and they're all highly intuitive. It seems like lattice structures here restrict our symmetries. A theory set on a square lattice could only have the symmetries of that lattice, like discrete shifts and quarter turns and certain mirror reflections. And similarly for a hexagonal lattice, but with 1/6 rotation. So it seems like the lattice is what's doing the work to restrict our symmetries in this way. It also seems like the lattice in these theories is helping us distinguish the theories. Two theories with different lattices, if one's square and one's hexagonal, those certainly can't be equivalent to each other. As I just mentioned, they have different symmetries and they seem to have very different commitments about what the structure of the world is on this microscopic scale in terms of its space and time. Right. And it seems finally like lattices are fundamental. The lattice that a discrete theory is set on seems to be a very fundamental part of the theory. It's what the fundamental fields phi are defined over, They take lattice sites and maybe times and map them onto values, here temperatures, right? Also, it seems to play a non-eliminable role in determining and capturing the theory's symmetries. So it really seems like these lattices are baked in and are doing very substantive work in these lattice theories, and so we ought to take them seriously as part of the real commitment of what that theory is when it says what the world is like. Right? However, in this paper, I discuss how none of that's true. None of the three intuitive points made on the last slide turn out to be true. In fact, I argue for a very rich analogy between lattice structures that appear in our discrete spacetime theories and coordinate systems which appear in our continuum spacetime theories. So lattice structures are analogous to coordinate systems, is what I'm saying. And this analogy is confirmed in three ways in the paper. First, neither restrict symmetries. As I show, theories set on a lattice, in fact, can and do have continuous translation and continuous rotation symmetries. So lattice structures don't restrict symmetries in the same way that coordinate systems don't restrict our symmetries. You can have a rotation invariant physical system set in Cartesian coordinates. You don't have to match up the coordinate system with the symmetries of the theory. That might be nice to do sometimes, but you certainly don't have to. Secondly, both lattice structures and coordinate systems are interchangeable. Given a theory described with some lattice structure, I can always switch it to another. You give me your favorite square lattice theory, I will give you an equivalent hexagonal lattice theory. And this interchange is just as easy as switching coordinates. Really, it's very analogous. And both here are ultimately optional. Right? Given a theory described on some lattice, we can always reformulate it to reference no lattice at all. In fact, that's analogous to the fact that we can give a continuum theory a generally covariant, i.e. a coordinate-free formulation. And this is what the title of the talk is about. I'm here presenting a discrete analog of general covariance. Right. Ultimately, the goal of the paper is to show that lattice structures are coordinate-like representational artifacts. Right. In fact, that is the main lesson of the paper. Lattice structures are rather less like a fixed background structure or an underlying manifold, and they're rather more like a coordinate system, which is to say they're merely a representational artifact. Right. And this analogy has very significant consequences if taken seriously. The lattice structure supposedly underlying any discrete lattice theory ultimately has the same level of physical imports as coordinates do, which is to say none at all. Thus, the world can't be fundamentally set on a square lattice or any other lattice any more than it could be fundamentally set in a certain coordinate system. Like coordinate systems, lattice structures are just not the sorts of things that can be fundamental. They are both thoroughly representational wherever they appear. So ultimately, the conclusion is that spacetime cannot be discrete, even when it's representable as such. When you hand me a theory represented with a discrete spacetime, that's very nice and well, that may work, but that can't fundamentally be what's going on with your theory. All right, please enjoy the paper.